Hello everyone, today we are starting with a new series on hash maps and hash sets. So I hope that you are enjoying and learning something from all the series on data structures and algorithms till now. In case you have any feedback, good or critical, please do mention in the comment section. I would love to go through your feedback and make any changes or improvements if required. So this video will mostly focus on the advantages of using sets and maps and their concept and finally the implementation. In subsequent videos, as always, we'll try solving some problems together. So without any further ado, let's get started. Let's begin by discussing the best searching time complexity offered by different data structures to others. So first very obvious data structure is an array. Now in an unsorted array, we can insert an element in O1 time. So insertion takes O1 time. Now, why does it take O1 time? Because we can simply add the element in the end. But the searching time complexity is big O of n because we need to do a linear search in the complete array. Now, talking about a sorted array, the worst case time complexity for inserting an element in the array is big O of n. Because we need to insert elements at a particular position in a sorted array, and whenever we insert an element in between, all the subsequent elements need to be pushed by one place. So doing that shifting process actually takes big O of n time. But in a sorted array, we can search an element in log n time using binary search. Now let's discuss about a binary search tree. So the worst case time complexity for BSTs are obtained when the tree is completely skewed. So a skewed binary search tree is obtained when all the nodes are either on the left or on the right. In that case, the insertion and search time complexity is big O of n. And it is big O of n because in both the cases there's a possibility that we would have to parse all the nodes from root to leaf. Now an improvement would be using some kind of a balanced tree, so which does not become skewed. So in that case also the search and insertion would actually take big O of log n time. This is because we might have to traverse all the way from root to one of the leaves, and when the maximum length of this path will be equal to the height of the tree, and since it's a balanced tree, the height is going to be log n, where n is the total number of nodes. So traversing whole path actually takes big O of log n time. So why are we actually looking at these complexities? So insertion and searching are two very important operations. So there are multiple scenarios in which we might need to keep a track of the element that we have already encountered, or we need to keep a track of some info associated with a value and retrieve the info for that particular value in the most optimal way possible. So this is where hash sets and hash maps come into picture. Both both of these allow you to insert and search elements in big O of one time on an average. So what do I mean by average? It means that if we are doing a lot of insertions, there might be few operations in between that have a higher complexity than big O of 1. But if we take an average of the time complexity for all the operations, then the average would be big O of 1. So you will be able to understand the reason or logic behind this after we discuss the implementation of hash sets and hash maps. But till then, we can keep in mind that the average complexity for insertion and searching in sets and maps is actually big O of 1. So like a lot of other algorithms and data structures, both these data structures use the concept of hashing. Now let's discuss about hashing. What is actually hashing? Hashing is nothing but a technique to map arbitrary values to another value. Now this new value that we receive might be part of a predefined set of values or might be some arbitrary value itself. Let's understand this with an example. So a very simple or a naive hashing function is the modulus operator. Now if we take a mod with x, so we are given some value y and we take a mod with x, we obtain a new value and we call this new value as the hash of y. So we can see that how this modulus function is mapping y to a new value hash, and that's why this modulus is acting as a hashing function for us. Now when we take a mod with x, all the values or the hash values that we are going to get will be actually between 0 to x minus 1. So in this case, the value we actually received belongs to a predefined set of 0 to x minus 1. But let's change our hashing function a bit. So if we say that our hashing function is now y mod x raised to the power y, where y is the number and again x is some default or predefined value. Now we can say that the hash value can be anything, can be arbitrary. And why is it arbitrary? Because y in itself is arbitrary. Since we are raising y mod x to the power of y, the values that we are going to receive are also going to be arbitrary. They are not going to lie within some predefined set. So obviously they are going to be integers, but then there's no predefined sets of some values in which we can say that this value is actually going to lie. Now, there are a variety of hash functions available, and different hash functions are used for different use cases. Now that we have understood hashing, let's circle back to our original discussion. So we'll first discuss hash sets and then move on to hash maps. Let's assume that behind the scene, a hash set is an array. Now let's say that we have an array of size say 29. So there are cells in here. So let's put the index 0, 1, 2, 3, and then there's 28, 27, 26. So these are the indices for each cell, and this is an array of size 29. So is there any way to find out the position of any incoming element in O1 time using hashing in this array? There is actually. So we can take the modulo of the incoming value with the size of the array. Then we can map each value to an index in the array, and we would know the exact position of the element in an array in O1 time. So just to be clear, what I'm trying to say is that if I have an incoming value which is num, and I take modulo of num with the size of this array, in this case 29, then this num can actually be mapped to a particular cell in this array every time. Now, if we have already determined the position of an element in the array in O1 time, we can simply go to the index and insert an element in O1 time, and for searching, we can go to that cell and check if an element is present or not in just O1 time. So for example, let's say that we have 3 entries and we need to insert these 3 entries into our hash set, and let these 3 entries be 3, 29 and 31. We also assume that initially all cells will be holding some junk value like int min or something depending on your use case, and that value indicates that there's no element in that particular cell. So since I will not be able to fit int min in these cells right now, so let's assume that the junk value that we are using is -1. So -1 indicates that there's no value in these cells right now. So everything is initialized as -1. Now these values will be inserted at index 3, 0 and 2. Why is that? Because the index is determined by num mod 29, and when we do a modulus of these values with 29, this is the remainder that we get. So let's add these to our hash set. So 29 goes at 0 and again 31 goes at 2. So let's insert these values quickly. So 3 goes here, 31 goes here, and 29 is inserted at 0th index. Now if we need to search 29, I know that 29 if present will be available at 0 index. So I would go to 0 index and check if the value is equal to 29 or not. If the value is -1, I know that 29 is not present. But if the value at 0th index is 29, I know that 29 is actually present in my hash set and I can go and return true. So similarly, let's say I got a query to find 32 in this hash set. I need to return whether 32 is present in this hash set or not. So first I'll determine the index where 32 might be present. So 32 mod 29 gives me 3. So if 32 is present in my hash set, it is definitely going to be present at index 3. If it is not present at index 3, then it is definitely not present in the set altogether. So what I do is that I go to index 3 and check the value stored at index 3. It is definitely not equal to 32. That implies that 32 is not present in my set. So I'll return false from here. Now a very obvious doubt or concern that may come to your mind is that there may be multiple values getting mapped to the same index. So for instance, in this array of size 29, or in this set of size 29, I got multiple entries to insert, and two entries out of these multiple entries were 32 and 3, and now both 32 and 3 are going to be mapped to the same index 3. So how do we actually handle this case? We know that if we take modulo with a very big prime number, the chances of collision reduce significantly. But there are two major issues with this approach. So the first issue with this approach is that behind the scenes we would have to actually maintain a very big array which has size equal to this prime number, and that is just a waste of memory. And the second issue with this approach is that this just reduces the chances of collision, but still there may be a rare case, say 1 in million, when collision actually occurs, and that will again be a problem because we would have to keep track of two or more elements again in the same cell. So there are actually multiple techniques to handle these collisions like separate chaining, open addressing, double hashing, etc. We will discuss separate chaining, which is the most widely accepted technique in hash sets. So in this technique, each cell in our original array does not actually directly store the value, but points to a list or array of values, and we store the incoming values in these lists. So the arrangement looks something like this, that this is the original array, and we have cells going from 0, 1 all the way to 28, and each cell in this array is actually pointing to a list of numbers. So in the case where we have entries such as 0, 29, 3 and 32, the arrangement would look something like this. So 0 and 29 will be stored in this array, and we'll have a cell with index 3 that would be pointing to an array storing the values 3 and 32, and all other arrays similarly would be empty. So for further explanation, let's take a set which is smaller than 29, because it's really difficult to visualize all the cells in an array of size 29. So let's assume that the size of our set is 7. So we only need an array of size 7 to represent it. So 0, 1, 2, 3, 4, 5 and 6. And let's say that we want to insert values 1, 2, 3, 8, 9, 10. So the hash set would look something like this. So 1 would be inserted at cell index 1, 2 would be inserted at index 2, 3 would be inserted at index 3, 8 again. So this is an array of size 7. So we are going to take modulo with 7. So 8 is going to be inserted at index 1 again. 9 would be inserted at index 2, and 10 would be inserted at index 3. And all these would be pointing to some empty array of some kind. So just to clarify, in insertion what we have done is that we find the corresponding bucket of the value by taking a modulo with the size of the set or the array and add the value at the end of the array pointed by that bucket. So similarly, if we need to search, we find the bucket by doing a similar modulo operation and do a simple search in the array pointed by the bucket. So like if I need to find a value, say 11, so if present, 11 will be present at 4th index. So I will go at 4th index and I will traverse the array pointed by 4th index. So I will traverse this array and see if this array contains 11 or not. If this array contains 11, then my set has 11. If this array does not contain 11, then my set does not have 11. Now again, an obvious concern is that what if the size of the array pointed by any bucket becomes very large? So say we inserted values like 7, 14, 21, 28, 35, 49 and so on. You get the idea, right? We are inserting all the multiples of 7. Since these are all the multiples of 7, everything is going to go in the bucket pointed by index 0. And searching in, now if we have to search any multiple of 7 or anything that would actually fall in the bucket pointed by 0, the searching would become really inefficient. Why is that? Because we would have a very lengthy array and we would be essentially doing a linear search in that array, because these values are not coming in sorted order. So the values in the bucket are also not going to be in a sorted order. So then again we would be doing linear search on a very lengthy array, and then we would not get O1 time complexity on an average. But engineers, as always, have a solution for almost everything. So what we do is that we try to keep the size of all the arrays pointed by all the buckets smaller than a particular threshold. So for example, if we define a threshold of 5, then we will keep the size of each array less than or equal to 5. So as soon as the size of any array becomes greater than 5, we do some kind of processing. So before discussing what processing we do, just to mention here, we use something known as load factor for keeping track of the sizes. So load factor is nothing but an indicator of the size of the arrays or load on each bucket. And as soon as the load factor crosses a threshold, we perform this processing. So for easier understanding, I am taking into account the size of each bucket or the size of each array. But in implementation, we use something known as load factor, which is the average size. So we'll discuss more about the load factor when we are discussing the implementation. But for now, let's just assume that the criteria for processing is the size of each array. Now what we actually do is that we double the size of our array or set and distribute all the existing values in this new array. Now since we have a bigger set of buckets, the number of collisions will reduce because all the values that were supposed to come in the same bucket will actually get distributed in different buckets. And that's how we are actually going to reduce the collisions, and that's how we are actually going to reduce the size of each array. And this is actually much better than allocating a very big array right in the start, because we increase the size of our array on need basis. So let's try to understand this with an example. So again, I take an array of size 7. Now let's just insert elements 1 comma 2 comma 3 in this particular set. So it would look something like this. And let's also assume that the threshold for our set is 1. So if the size of any array becomes greater than 1, then we have to do our processing or rehashing. So now let's say that we got a query and we need to insert 8. Now if we are trying to insert 8, we know that this 8 is actually going to go inside the bucket for index 1. And in that case, the size of this bucket will become greater than 1, which is greater than the threshold. So now we need to do our processing, and the term for the processing or the technique is called rehashing. So we can say that we have to perform rehashing now. So as we have already discussed, what we'll do is that we'll double the size of our set or array. So if we double the size of our set or array, the set would look something like this: 1 2 3 4 5 6 7 8 till 13. So there will be 14 cells in this array now. Now we have to first distribute all the existing values again. So 1 2 3 are again going to be in the cell 1 2 and 3. Now we try to insert 8, and if we are trying to insert 8 in this new set, we'll take modulo with 14, and we see that the hash is now 8. So this will not go in this first index, but it will actually go in this 8th index. And when it is inserted in 8th index, the set would look something like this. Now we can easily appreciate the fact that by how doubling the size of our set and rehashing all the values, we can actually avoid increasing the size of one particular bucket by a very huge number. So we try to keep the size of each array below this threshold, and since size of each array is below this threshold, this, even if we do a linear search in these arrays, it is not very costly, because if the size of each array, say, is a constant value 10, and doing a linear search in an array of size 10 is not that inefficient, because big O of 10 is again big O of 1 operation. Also, we can now understand why some operations in between might be costly. So it is because of this rehashing while inserting that some operations might become costly. Because in rehashing, what we are doing is that all the existing values we have to distribute again in a new set, and doing that is an operation of and doing that actually takes time complexity big O of n. But we can see that even if in between there are some operations of complexity big O of n, almost all the other operations are going to be of complexity big O of 1. So we can say that while inserting the elements in a hash set, the average time complexity is big O of 1. Now, if we have understood hash sets, understanding hash maps will be very simple. In hash map, instead of a value, we have a key comma value pair. So we have something like this. Now we insert this key value pair in our arrays. So the arrangement would look something like this. So this is our bucket, which is pointing to arrays. And each array, instead of just storing a value, will be storing key value pairs. So each cell in this array would look something like this, and similarly here as well. So all the buckets will be pointing to an array storing key value pairs. Now hashing is always done on the key. So finding a bucket for insertion and search is always done on the basis of the key in this pair. Value is just additional info associated with the key which we are storing in our memory. So for example, a use case could be that key is the roll number of a student, and the value that we are storing along with the key is a struct which is storing the student's name, address, class, etc. Again, since the searching and insertion is dependent on just one value, which is the key in the pair, the time complexity is exactly the same. It's just that hash maps have a little higher space complexity when it comes to, because now we are storing a pair instead of just a value. But the processing and the time complexity is exactly same as hash sets. Now I think we have discussed the concept in detail, so it's time to move on to the implementation of hash sets. So we are going to understand the implementation of a hash set, and I've already written down the complete code for it, so it'll be easier to go through the code line by line and explain every aspect of this implementation. Now first let's discuss the data members of this class. So buckets is a vector of vector. So as we know that, let's recall what is the structure of buckets. So buckets is nothing but an array which points to the array storing values. So each index in this buckets is actually pointing to an array which are in turn actually storing the values. Now this is nothing but a staggered 2D matrix. So what is the concept of a matrix? So actually each row is pointing to a array whose size is equal to the number of columns in that matrix. And what is a staggered 2D matrix? A staggered 2D matrix is when the size of each row is not same, with the size of each row is varying. So from this image, we can easily understand that behind the scenes, our main structure holding the data is a staggered 2D matrix. So we define this 2D matrix as a vector of vector. Now int size is going to store the total size of the set, or the total number of values that have been inserted in the set till now. Or you can also refer it to as the sum of the size of all the arrays. But a more simpler way is that size actually stores the total number of values that have been inserted into this set till now. And we have something known as a predefined threshold. So we already discussed that we define a default threshold, and if our value goes beyond this threshold, we do the rehashing. So, and we also discussed that we call it the load factor. So we have defined the load factor as 0.75 by default, and load factor is nothing but the average size of array. So we'll look at the exact formula to calculate the load factor as we move. So now this is nothing but the constructor. So in this constructor, we actually initialize our buckets vector. So what we are trying to say is that the total number of different indices that are going to be there in buckets. So basically when we are determining the bucket, or in our hash function, we actually take mod with the size of the bucket. So what are the different numbers of buckets that are going to exist? So this S parameter actually is defining that what are going to be the different number of buckets in our set, so, or the size of the set in general. So we are initializing our 2D matrix, and we are initializing the size data member because there is no element inserted into this set yet, so it is initialized as 0. Now this is the helper method, which basically returns the hash for any value. So as we have already discussed, that hash is nothing but the modulo of value with the size of the buckets, or the different number of buckets that are existing. So what we have done is that we get a value, we take the modulo with buckets dot size, which is the total number of buckets existing, and we return this value as the hash. Now the first function that we are going to discuss for this data structure is the find function. So find function basically returns true if this value is present in our set, and it returns false if the value is not present in our data set. And what we try to do is that we try to maintain the time complexity of this find function as big O of 1. So as parameter, we are getting the value which we need to find out. So the first thing we need to determine is that if this value exists, then in which bucket this is going to exist. So simply we take the hash of this value and get the bucket in which this value is supposed to exist, if at all it is present in the set. Now we extract the array being pointed by this bucket. So if this value is present, it is going to be present in the array pointed by this particular index. So we take the array or the vector being pointed by that particular index, and we just do a linear search on that array. So we traverse every element in the array and we check that whether every element in the array, or is there any element which is equal to the value that we are trying to find. If we find an element in the array which is equal to the value that we are trying to find, we return 1, or return 1 is same as returning true. Since we get a little confused like how to write true, is it all caps, is it first letter caps, because there, or is it all small, because in every language there's a different way of writing true. So what I do is that I just return 1 or return 0, because as we know that 1 represents true value, so a 0 represents false value and any non-zero value represents true. So I return 1 when I have to return true, and I return 0 when I have to return false. So if we are able to find this value in the array, then we return 1. If we are not able to find the value in the array, this loop will end and we'll come here and we'll return false. Now, as we have already discussed, due to the load factor and the rehashing technique that we follow, the size of this array pointed by this bucket is actually going to be within a particular limit or within a particular threshold. So that's why this loop for linear search will not be very costly, and the total time complexity for this method is actually going to be big O of 1, or big O of constant. Now the next important method that we have to discuss in hash set is the erase or the delete method. So what it does is that it takes input as the value, and if that value is present in our map, it will delete that value. If that value is not present in the set, it will do nothing and just return. So as always, we first need to determine the index or the bucket where this value is going to be present. So we take the hash. Again, we take the array that is being pointed by this particular index, because if this value is present, it is going to be present in the array, and we have made a temporary vector. So essentially what we are trying to do here is that we are going to pick each element in this array being pointed by the bucket, and we are going to compare this element with the value that we want to delete. If this element is equal to the value that we want to delete, we will not add it to the temporary vector, otherwise we'll add it to the temporary vector, and then we'll start pointing to this temporary vector. So by doing that, we have removed the value from our vector in case if it was present. In case if it was not present, then the temporary vector would be similar to the initial vector, and essentially we'll be again pointing to the same vector. So that's what we have done. We are just picking elements one by one from our original array, and we are comparing these elements with the value that we want to delete. So if in case it's not equal, we are pushing the value to the temporary vector. In case if it's equal, we know that this value needs to be removed, so we do not add it to the temporary vector. Also, we have found this value in the maps. This value exists in the map, and this value will be removed in the map after this processing. So the size or the total number of elements that are stored in the map should be reduced by 1. So similarly, we have done a size minus minus here. So after this complete loop, what will happen is that we will have a new array, and that array will not be containing this value that we were trying to delete. So now our bucket will start pointing to this new array. Now we have already discussed that while inserting, we check the threshold. If the threshold has been breached, we do processing known as rehashing. So before moving to the insert method, let's discuss a helper function rehash. And this rehash helper function will actually be called by the insert method if the threshold has been breached. So it'll be easier to first understand this rehash method and then move to insertion, because that would make insertion very easy to understand. So we have already discussed that in rehashing, what we do is that we increase the size of the bucket or increase the size of the set by 2 times. We double the size, and we distribute all the existing values in this new set, and the incoming value also is added in this new set now. So by doing that, what we essentially do is that we reduce the size of each array being pointed by the buckets. So that is the similar thing what we have done. We first find the new size, what is going to be the new size of the set. So the earlier size was represented by buckets dot size, because that was the total number of buckets we have, but we now want twice the number of buckets. So the new size for the set is going to be 2 into the already existing set. And then we create a temporary set. So this temporary set, we are going to store all the values, and then we are going to replace the original set with this set. So now we first need to distribute all the existing values in this new set. To distribute all the values in the existing set in this new set, we have to traverse the whole set. So we have already discussed that old set behind the scenes is nothing but a staggered 2D matrix. So we are using the 2 for loops to traverse the whole set. So first loop is obviously going from 0 to the total number of buckets, and the second loop goes from 0 to the size of each bucket that we are referring. Now we take out each value from the set or from the 2D matrix buckets. We find the new hash value for this value. So while finding the new hash value, we have to take modulo with the new size, not the old size, and then we add this value to our new set. So hash represents the new bucket that it is going to go into, and that bucket is pointing to a vector. So we take out the bucket and we add this value to the vector being pointed by that bucket. And in the last, what we do is that we just replace the existing set with the new set that we have just created, which has a size twice of the existing set. Now that we have discussed the helper method, it will be really easy to understand the insert method. So in insert method, as obviously we receive a parameter which is the value, and this is the value that we are trying to insert into our set. So first thing that we do is that we find whether this value is already existing in my set or not. So this is one thing that we might have missed or might have not discussed. The keys in map are actually unique, and the values in set are also unique. So they cannot be two entries with the same key in a hash map, and they cannot be two entries with the same value in a hash set. So by this logic, we first need to find out whether this value is already existing in my map or in my map slash set or not. If it is already existing in the set, I do not insert it. So I call my find method and check whether this value is already existing or not. So find returns true if it's already existing and false if it is not. So in case if it returns false, then we have to do all this computation or insert it into the map. If it's not, then we can simply skip all this and return from this method. Now what we do is that first we will find the bucket in which this value needs to be inserted. So hash method or the hash helper method returns the bucket in which this value needs to go, and we simply add this value in the bucket where it had to go in. So we have taken out the hash or the bucket where it has to go, and we simply add this value to the bucket, and we increase the size by 1. So since we have added a new element, obviously size data member will be increased by 1, which is keeping track of total elements that have been inserted into the set till now. Now what we do is we find the load for this particular set. So load, as I said, is actually the average size of each array pointed by the buckets. So how, according to you, will we find the average size of each array? So average size of each array will be nothing but sum of all the arrays divided by the number of arrays. So we have already discussed that the sum of all the arrays is going to be equal to the size data member, because size is actually storing the total number of elements, and the sum of size of each array will be equal to the total number of elements present in the set till now. And what are going to be the number of arrays? So the total number of different arrays that exist is equal to the total number of buckets that we have, because each bucket is pointing to a separate array. So this formula is basically going to give us the average size of each array, or also referred to as the load factor. So we have found the load for our existing set. Now if this load goes beyond the load factor, the predefined load factor, which is 0.75 in this case, then we call the rehash helper method. Rehash helper method helps us to reduce the load, as we have already discussed. So we find the load. So what we are doing, we first check whether the element is already present or not. If it's not present, we insert it into the set and find the load for our new set. If this load breaches the predefined threshold, we do a rehash. Otherwise, if the load has not gone beyond a threshold, we don't have to do anything, and we simply return after inserting the element. So that's all for the implementation of a hash set. Now again, a question. So do we need to write this code every time we want to use a map or a set? Actually no, and considering how frequently we use maps, it would actually be a real pain if we always have to write this boilerplate code. So every language again offers maps and sets, and in Java we have something known as hash maps, immutable maps, etc. In C++ as well, we have two flavors of maps and sets. So one is the unordered set and unordered map, and the other is simply a map and a set. Now what is the difference? So if I traverse a map or a set, I will get keys in increasing order. That is, keys are stored in a sorted order in a map or set. So to do this, actually they use some kind of a balanced tree based approach, and due to that the time complexity is not O1 but actually big O of log n. So even though they are called map and set, they are a tad bit different from the conventional ones. While the unordered map and the unordered set, as the name suggests, does not store keys in sorted order and are very close to the implementation that we just discussed above. So due to this, they offer a time complexity of big O of 1. So just keep this in mind, because in most cases you would need an unordered variant to quickly insert and search, and in that case you would actually be using a unordered set or a unordered map. Now in Python, I think dictionaries are equivalent of maps. They definitely have the same functionality, but I have never cared to look at the time complexity. So if you code in Python extensively, then this might be an exercise for you to Google the time complexities for a dictionary. And I guess with this, we have reached the end of this video. I hope you found this helpful. In the next upcoming videos, we will be solving some problems on maps and sets. So hope to see you in the next video. And thanks for watching. Bye bye.